Now we're getting to the part of actually training the model itself. Remember that we first came from collecting the data set and learning about speech commands. And then we learned about how to pre-process the input data that we have, which is in the form of raw audio files, which are then getting converted into a representation that is actually useful for our neural network to be able to ingest. Now we're going to focus on designing the model, and we're going to think about how we should design the model for TinyML specifically. Now, because we are dealing with an image, it should not come as a surprise that we might just want to use a convolutional neural network at this point. We've used convolutional neural networks previously in order to classify things such as MNIST digits or the fashion data set, or in terms of telling horses versus humans. We've used it in different ways. Well, can't we just reuse it? Well, what do you think? We've got an image which we create into a big tensor, and then we feed it into the network. And the network is effectively using a series of filters via convolutions to extract out interesting features, and then classifying those features to get some interesting outputs. That's all we're doing. And if that's the case, and if we're just dealing with an image, why don't we just replace that image with our spectrograms? Voila. Spectrograms have interesting features. Perhaps our network can actually piggyback on the exact same setup that we have, and then be able to extract interesting features out of it in order to do classification. And then we might be able to classify as, whether the word which came out from the microphone is into an analog signal that was then converted to a digital signal, which then got processed through FFTs and then came through here as a spectrogram, is a yes or a no, or pick your favorite word, Siri, Alexa, Google, whatnot, right? Well, we can reuse that model, can't we, that we touched on earlier? Well, yes, of course. Well, that's what this network has over here. Let's see the two parts. The first part and the second part are what we're going to focus on. The first part, the 5 convolutional layers plus pooling layers, are all designed to extract features of that image, right? And then we're going to be using a dense layer in order to help us do classification at the bottom. Those are the two major portions. Can we use this on the spectrogram? What do you think? Of course, the answer is yes, it's an image too. So if we look at a real device, we've only got 256 kilobytes of RAM, and we only have 1 megabyte of flash or storage on the device. Well, that might prove to be a little bit of a problem for this particular network. Why? Well, if you look at the model that we have, converting it into a TensorFlow model that's already saved into a TF Lite model, anytime you want to try and do something for development, we do the conversion, which simplifies the whole model down to a leanest and meanest form. And then we can print the size out. And voila, okay, well, that's 6,800 kilobytes. You think we have a problem? The answer is yes. We only have 256 kilobytes of RAM, and we only have 1 megabyte or 1,024 kilobytes of flash for storage. The model can't even be loaded onto the device. Forget about running it on the device. Don't worry. I know you're thinking, I know just how to quantize the network. Very well, sure. Pick your favorite quantization approach. Post-training quantization for our particular network here. At this point, you're a ninja at these things, right? Well, let's say that we do this quantization process, and then we end up with a model that's 1,700 kilobytes. It doesn't fit. Not yet, right? So, well, and we only have 1 megabyte of storage, right? And at best, we have 256 kilobytes of working RAM, and that's the whole RAM, right? Not just for the model, it's for all the software, the libraries, and the glue code, everything. So we've got a bit of a problem, because even though our network is really simple and we've tried to compress it down, it's still too big. So what can we do? We need to do something different over here. Well, we need something smaller. And the key thing that I want you to take away from this lesson is that when you're designing TinyML applications, they are very application specific. They just need to perform one task, and they just need to do it well. And that's typically the critical key. The secret sauce over here is actually enabling models to be really small that can run efficiently on embedded microcontrollers to just do that one thing well. So there comes the TinyConv model, right? It's still a convolutional model because we still are going to be using the spectrograms of, from that we got originally. It just happens to be a really tiny model. Look, you can come up with many different kinds of models. I'm just going to toss one out there for you so we can get started. It's a very simple network, in what we have over here. It's just one convolutional network followed by one dense layer for doing classification. And it gives you the probability of the word, yes or no, or the keyword that we're looking at, whether it's true or not true. And that's all it does. Really, really simple. So you take the input data, which again is pre-processed input data that we looked at in the previous videos, and then it goes through the convolutional operations, and then it goes through the fully connected layers and comes out of your output classification. It's simple by design because all we are doing here is trying to detect very simple words. You're not doing full-on speech recognition, and those things are much, much more complicated, and they have very deep networks. Now, certainly we can improve on this network quite a bit, and we'll get there at some point. But for now, I want to give you a baseline to start off with. And if you look at this network, it's got only 16,652 parameters, which is very, very small. And one of the things, by the way, I want you to take away also from this slide is to learn how to calculate the number of parameters that are involved, because those parameters or weights are effectively that give you a key sense of the size of the network, right? How big is the network? In future, you're going to need this to be able to calculate these things, whether it's for a quiz or whether you're actually using it for actually doing your project. So if you look at the amount of the parameters, the size of the parameters that this leads to, it's about 70 kilobytes. That's pretty good. Well, if we quantize it down, well, it's going to be come all the way down to 17 kilobytes, right? That's about 1/4 the size of a 70 kilobyte model. And that's incredibly exciting. So that said, can I fit this on the network onto my device? The answer is absolutely yes. And that's the exciting part about it, which is the nice thing about this tiny con model is that it's not only just small, but it also leads to really fast inference. It's going to be very fast because we have very few number of parameters in the network, and we only have like very simple convolutional layers followed by a dense layer. So there aren't going to be many multiply accumulates that you have to do, and it has to be simple, which means your network calculations also need to be simple because you want to keep the inference fast. So the key takeaway here that I've given you a baseline network that will allow you to do some sort of classifications on keywords. The crucial reason that it has to be so small is because it's highly specialized, right? So it can't classify, two other keywords. It can just do these select keywords. So that's the thing I really want you to take away. I don't care if you don't remember the network specifics. What I really care about is that you remember that the network can be small because we are performing highly specialized tasks. So again, this is where you really want to understand what is the specific task you're trying to perform and try and specialize the networks for just that task, because that's what will allow you to become small and effective in deploying it on the microcontroller class of devices. And that's the essence of designing a model for keyword spotting on TinyML.